Welcome to Unit 5. We're starting off with Topic 5.01, History of Atomic Structure. Before we get to where we're going, it's kind of nice to have a look back, a little retrospective at where we've been. And I've already given this to you in a previous video to a small degree, but let's delve into it a little bit more deeply here, shall we? How did we get to where we are now? Well, first, you have to understand what a model is. Now, a model is simply a representation of real world phenomena based on observation and inference. Even a fashion model, when they wear clothing, is a representation of how that clothing is going to look when you're wearing it. So, what are some examples of these models? Well, we're going to take a look at those with respect to the atom. They represent our best mental picture of what reality is. Now, obviously, you're not going to look like a model wearing the clothing unless you just happen to be the model wearing the clothing. The rest of us just aren't going to look like that. So, it's a representation of reality. It's our closest picture to what it's going to come to. A scientific model is built up over a very long period of time by applying the scientific method over and over and over again. And each time an experiment is done and attempts are made to throw everything they can to test the model gets refined and more detailed. And that's exactly what I'm going to show you in two examples today. And it can take many different forms. It can be something as simple as a picture, or it can even be a graph, which is how you're going to be dealing with modeling this year in lab, using that graph to create a math formula, or something artistic, a sculpture, a painting, or even poetry. You can have an evocative, emotional model. This is a map of the New World in 1571. Now, the only technology they had available to them was ships and various tools to measure the position of the sun and stars and which direction was north and so on. And you'll notice here Florida and Cuba, and this is Lake Erie and Lake Ontario, which apparently open up into the Arctic. And I guess this is Long Island here, and Hispaniola, and up here is Nova Scotia, I guess. Here is the Mississippi River, maybe. I don't know. And then apparently we have mountains that run all the way into the middle of the country. I'm assuming that these are the Appalachians here. And then, of course, we have the Rocky Mountains over here. And west of the Rockies, there's just ocean because, California was still under the ocean at that time. We have India Superior up here. And then, of course, over here we have Hispaniola and Hispania, right. We have Spain up here and Portugal, and then Africa right here. And of course, South America looks like somebody sat on it. So there's all kinds of problems with this map, although it does show you the technology that was used to make it. So, how did we improve our picture of the Earth? Well, you see, if you're on a boat, you're on the same plane as the Earth, and it's really hard to read a page on a book if your eye is at page level. But if you can get yourself somehow above it, it makes it a lot easier to see. So, by the 1940s, we had airplanes. And with airplanes, we have a much better picture of what things look like. It's not perfect, of course. Some of these shapes are still exaggerated or not quite right, but they got the job done. But shortly after this, we started launching satellites that could get you way up high above the Earth. And with that, imaging and mapping became a whole lot better. So the model improved. Google Earth is the most comprehensive model of the planet there is. You can even get right down into street level. You can go into some buildings even and walk around. It's not reality. It's just a representation of reality. Scientific discoveries lead to advances in technology, and those advances in technology in turn lead to additional scientific discoveries. It is a cycle that has led us to great discoveries and great technology. And with this comes better and better models of how the universe works. One of those was applied to atoms. Couple of thousand years ago, we had no idea what atoms were, but there were a couple of Greeks that hypothesized that all matter is pixelated. Take a look at a computer screen, especially one that's not 4K, or look at your TV. You'll notice that there are individual dots on the screen, and these are called pixels or picture elements. And they figured that matter was pixelated, that, you look at a whole picture and it looks like a solid thing. But if you were to zoom in really, really small, you would see it's made up of smaller constituent parts that are just too small to be seen by the eye. And you would not be able to break up those tiniest particles any further. Now, of course, this was just a thought experiment, but it was pretty prescient. Things exist, and they must be made of smaller pieces, and the smallest possible pieces must be indivisible. And the Greek word for indivisible is atomos, which is where we get our word atom from. Now, again, there was no actual experiment done here. It's okay, well, let's contemplate the universe. Then a couple thousand years went by and not a whole lot was being done. There was experiments being done. People tried to turn base metals into gold, but they weren't publishing their results, so the field of chemistry didn't really advance much over this time. But in 1803, and right after the discovery of the battery, the fact that you could put a battery together and create an electric current, that electric current was used to decompose compounds into their original elements. And this is when a lot of things became interesting. John Dalton witnessed the decomposition of water using electricity and measured the mass of the hydrogen formed and the mass of the oxygen formed multiple times. And they always came up with 8 grams of oxygen for every 1 gram of hydrogen in water, always. And this led to the law of definite composition, which states that the ratio by mass of elements in a compound is always the same whole number ratio. And he used this idea and the law of multiple proportions, to come up with the concept of atomic mass. And he created a chart of atomic masses. Hydrogen has a mass of 1, and carbon has a mass of 6. Oxygen has a mass of, actually, an atom of oxygen has a mass of 6, but a molecule of oxygen has a mass of 18. The formula of water is H2O, and the way they arrived at that is there's twice as much hydrogen formed as oxygen. And they knew that equal volumes will contain equal number of molecules, so double the volume must contain double the number of molecules, H2O. Thank you, Avogadro. These are some of the symbols that he created to represent atoms and the compounds that they form. So his model was that the atom is a solid indestructible sphere, and all atoms of the same element have the same atomic mass, which is different from the mass of all other elements. These are actual models that he created to actually model his molecules. Some of you may have played with these molecular models on your own. We can still build molecules today using these as representations for an atom. Then things started to happen really, really fast. J.J. Thomson made use of electricity to do a slightly different experiment. His technology was the cathode ray tube, which would later go on to become the television screen. You may have seen those big chunky TVs, not the little flat screen LEDs or LCDs, but the big chunky cathode ray tube TVs. They were standard for a very long time. LED and LCD TVs are relatively recent. This is where the picture would be on the screen. And the source of electricity was at the back. And he found that when you shot this beam of electricity, that it would cause the screen to glow because it was covered in the same stuff that Rutherford used to figure out what charge particles were, as you might have seen in a previous video. And you can actually use electric current, electric charge to shape the beam. And it turns out that these beams are pulled towards negative charges. I'm sorry, they're pulled towards positive charges, meaning that the beams themselves must be made of negative particles. And since these are particles of electricity, they were these cathode rays, as they were called at the time, were called electrons. You can see here how a magnet can actually push or pull the beam of electrons, either attract or repel. The electrons are attracted to positive and repelled by negative, which means that they are negatively charged. Now, up to this point, it was assumed that electric current was a flow of positive charge, so you can understand how this might have really upset and confused people. Because this electricity has to come from somewhere, this fundamental particle, the electron, must be part of the atom, which means atoms are not indivisible. They have parts that you can remove, these parts called electrons. Now, they knew that atoms themselves have no electric charge, so if electrons are negative, then whatever the rest of the atom is made of must be positively charged. So his model was that the atom is a diffuse sphere, positively charged sphere with negatively charged electrons embedded in it. The name for the model was originally the plum pudding model, where these would be raisins embedded into plum pudding. A more recent concept would be the chocolate chip cookie dough model. A chocolate chip cookie dough ball has positively charged cookie dough, and the chocolate chips themselves are negatively charged. Actually, they look a little bit more like Reese's Pieces, but never mind. So that's the Thompson model of the atom. Then, a short time later, Ernest Rutherford, that dashing New Zealander — no, I do not have a crush on him, besides he's dead. The technology, of course, was his discovery of alpha particles. And, he used these alpha particles to test the electric charge of these particles. He used them to do artificial transmutation. What else could this genius do with these alpha particles? Well, what he did was he shot them at thin pieces of metal foil, specifically gold, because gold can be flattened thinner than any other metal. And he wanted to see what results he would get. Now, the results he got were very intriguing. Here is your source of radioactivity. There's a pinhole in one side so that only the alpha particles traveling in this direction can escape. They move into the gold foil, and you would expect that if the atoms were solid, then all the alpha particles would just bounce off. If the atoms were foggy or diffuse, then all the alpha particles would just go straight through. But what he found was a combination. Most of the particles went right through, which hinted that atoms are actually made of mostly nothing at all. But a few of them bounced back or were deflected, meaning that there is something hard inside the atom for the alpha particles to bounce off of or be deflected from. Now, since alpha particles are positively charged, if the thing in the atom was negatively charged, then these positive alpha particles would just stick to them and they would never bounce off or come out the other side. Which means whatever these alpha particles were deflecting off of must have a positive charge. So Rutherford discovered what Thomson didn't know, the nature of the positive charge inside the atom. And his model was that the atom is mostly made of empty space. Most of the alpha particles went right through, with the positive and negative charges separated instead of all mixed together. And to be more specific, all the positive charge is concentrated in the center of the atom as a nucleus, so that the alpha particles that just pass right through are passing through the empty space in the atom, not the empty space between the atoms, but the empty space that the atom is mostly made of. Now, this is a gross exaggeration as to the size of the nucleus. The nucleus is about 1/2000th the size of the rest of the atom, so only about 1 in every 20,000 alpha particles would bounce off. So his model was a positively charged nucleus, 1/20,000th the diameter of the atom, but containing all of its mass. So the nucleus has all the mass, which you learned about in the previous unit between the protons and the neutrons. Of course, in Ernest Rutherford's time, protons and neutrons had not yet been discovered. And you have electrons orbiting around, but most of the space inside of an atom is completely empty. Imagine a stadium that has a baseball sitting on the stage, a couple of flies buzzing around, and the rest of the stadium or theater is completely empty. very quiet. Here's his gold foil experiment. I'll show you an animation. So in Thomson's model, the electrons were uniformly distributed throughout a uniformly positively charged sphere. He predicted that the atom was actually very diffuse, where the charges are spread out. Just waiting for the clip to advance a little bit. Now, when Rutherford did his gold foil experiment and shot the alpha particles at this is still playing. Okay. He was expecting, because Thomson said that the atom is mostly diffuse, that the alpha particles would all just simply pass right through the atoms without being deflected at all. Or any deflections would be very, very minor. So you can see here the alpha particles in his prediction would go just right through the alpha particles. Would go right through the gold foil without any bouncing off. That's what he expected to happen if the atom actually was diffuse. But this is what actually happened. Most went right through, but a few deflected. Now, why would they deflect? Well, they would deflect if they hit something. What they hit must be very small because very few of them deflect, and what they're hitting must be positive because they're repelling the positively charged alpha particles. Based on this gold foil experiment, he discovered that atoms are mostly empty space and that there is a small, dense positive nucleus in the center of the atom. This revolutionized our view of what the universe is made of. So, what about the size of that nucleus? Well, if we were to zoom in on an atom, get closer and closer and closer, we would have to get pretty far before we started coming across the nucleus. Where is it? Oh, I think I'm starting to see it there. Yep, there it is. There's the nucleus. So you can see if you fire alpha particles at this atom, only a tiny number are going to hit that nucleus. It's kind of like putting a matchstick on top of a table and just generally firing blindly in the direction of the matchstick. Chances are you're never going to hit that matchstick. Maybe one out of every 20,000 shots you fire is going to hit that matchstick because it's so tiny. 2 years later, Niels Bohr was doing some experimentations with spectroscopy. What happens is, if you know how a rainbow works, right? Like light passes through a raindrop, and the raindrop bends the light beam and separates light into its component wavelengths: red, orange, yellow, green, blue, and violet. Well, as you're going to see in the next topic, light is formed when electrons fall from higher to lower energy levels, and every element has its own unique pattern of light being formed. And how is this light formed? Well, the energy has to come from somewhere. So Niels Bohr, based on these spectral lines, this is what the spectral lines look like. More about that in the next topic. Must be from electrons dropping in energy levels. Now, what energy levels? He hypothesized the energy levels. And based on experiments, we now know that electrons will contain certain amounts of energy. And if the amount of energy an electron has drops, the lost energy is released in the form of light. And for elements, it's always released in the same colors of light. A model that he came up with is basically the same as the Rutherford model. You have a small, dense positive nucleus in the middle, mostly empty space, except instead of not knowing where the electrons are, he said they're organized into these shells, these energy levels. And the further from the nucleus an electron is, the more energy that electron will have. So if it falls to a lower energy level, it will give off the energy in the form of light. You may recognize the Bohr model of the atom here, showing electrons in their electron shells. Since then, we've come up with far more complex theories using finely detailed spectroscopy, ionization energy, double slit experiments, and other things. And we have a clearer picture of what the atom looks like, except now what an atom looks like is a lot more complicated than we ever imagined. Energy levels are not enough to explain elemental spectra. Atoms not only have energy levels, those energy levels are broken up into sublevels, and those sublevels further broken up into orbitals. And those orbitals are regions of space not where you will find the electron, but where you're most likely to find the electron. You see, let's say you have a friend who works in your state and they move around from day to day. You never know where they're going to be next, you never know where they are. If somebody asks you where this person is, you can't pin them down. All you can say is they're somewhere in the state. And that's what an orbital is. It's a region of space around the nucleus where you're most likely to find an electron of any given energy. The Schrödinger wave equation describes those shapes. So when you solve for the Schrödinger wave equation, you don't actually get the exact location and direction that an electron is moving. What you get instead, thanks to Erwin Schrödinger, is a region of space where that electron is most likely to be found. That's the Schrödinger wave equation. Then we have Werner Heisenberg, who came up with the Heisenberg uncertainty principle that says that any effort you make to figure out where an electron is will change its location. And any attempt you make to figure out what direction electron is going will change the direction of an electron. So you cannot know with any certainty both the direction and location of an electron. And then Louis de Broglie came up with the idea that all particles travel in waves. The larger the particle, the less noticeable its wave function is. So let me show you how this applies to a very simple element, helium. What we're going to do is map out the location of where electrons have been located as it moves around the atom. We can detect where they've been, but we have no idea where they're going to end up next. So all we're doing is we're just recording where we found the electron. And as you can see, over time, we're starting to build up a picture of that region of space where we are most likely to find that electron. In the case of this electron, it is describing a roughly spherical shape around the nucleus. This, by the way, is known as an s orbital, and you'll learn about that when we do electron configuration. Now, it is actually theoretically possible for the electron to actually appear thousands of miles away for a brief instant before ending up back in the atom. It's all about probabilities. The chances of the electron being in this region of space are huge. Not quite 100%, but almost 100%. The chance of an electron occurring here is extremely small. Occurring here, even less, and even less the further away from the atom you get. So the vast majority of the time, you can expect to find the electron in this region of space. You do not know where it's going next, but you do know that you have the best chance of finding it in that region of space. This is also known as a probability cloud. Quantum mechanics, what a delight. And that is the history of our model of the atom from the Greeks to modern day. Once again, I hope this has been helpful and informative to you. And next time, we're going to take a look at how light forms. And until then, as always, please stay healthy, please stay well, and please keep on being swell. And once and for all, bye.